Welcome. In this video, we will take a look at a few more limits from chapter 2.2 with some algebraic limits. The first one that we'll consider here is the limit as x approaches 9 of the function square root of x minus 3 and x over x minus 9. We consider this one a little closer. We do have kind of a disguised difference of squares here on the bottom. One way I can express this function is, again, rewriting this limit. So the limit goes to, as x goes to 9, we have the square root of x minus 3 divided by, if I considered x minus 3 as a difference of squares, we can actually rewrite this as the square root of x, that's the square root of the first item, plus the square root of 9 would be 3. There is one factor. And then the difference of squares would be the square root of x minus 3. This would give us the conjugate pair term that would then multiply to get back to x minus 9. You could pause the video right now and just confirm that if you'd like. But these would be the conjugate pairs that would actually multiply to get x minus 9. Now, with this in view, we can now see where some cancellations can happen with our limit. Both x minus 3 terms can be found in the numerator and denominator. So these can actually be canceled to 1. And we're left with the final limit as x goes to 9 of the 1 over square root of x plus 3 ratio. So when we take that and evaluate this now at 9, we can see that this new function is continuous at 9, and we can evaluate this. So the square root of 9 plus 3, or 1 over 3 plus 3, gives us 1 over 6. So that would be the limit for part I. So let's take a look at this second question in J. Come down below here. We're going to consider the limit as x goes to negative infinity of this quotient. So we'll start with the square root of x squared plus 7x, and then divide by that 4 minus negative 2x. So let's just consider for this top function what is going on when x gets really, really large in the negative direction. So for instance, if we get really, really large in this negative direction, comparing these two terms, x squared and 7x, if we inputted, say, negative a billion, negative 10 billion, this 7x here is actually not going to carry much weight at all in this calculation. That x squared is going to be the largest term there. It's going to overpower that value very quickly. So we can kind of consider this as a really, really big negative quantity squared inside that square root function. So we essentially have a square root of a negative large number, let's say something large, quantity squared, divided by, if we considered, well, this is just going to be 4 minus 2, quantity something negative very large. If I plug that in, I'd have negative 2 times something very, very large, negative large, we could say. Something very huge. Well, notice that we want to consider these negatives here. If I have the square root of something negative large, that's just going to be really a positive large squared. And with that square root, we're just going to get some large value. Divided by, well, this 4 here, if we have something really, really large here, that's not going to really impact this expression very much. And this actually is not going to, again, give us much in terms of that denominator. So we can kind of ignore that small little bit. If you had $1 billion and somebody said, here's 4 more, it would not be very, would not move the needle very much for you. But we do have these 2 negatives that are important. We have -2 times this negative large value. So we can consider this as really 2 times the large quantity that we had here. We'll keep that kind of ratio there. 2 times something large here. So when we get done with this, we have a square root of something large squared, which that square root and the squared would cancel out. And we would consider this as just something large over 2 times something very large, that same large value. So when we consider large over 2 times large, well, this really just going to break down the ratio here to 1/2. So 1/2. That denominator, again, is going to be 2 times as large as our numerator, as this value, again, this large value gets bigger and bigger and bigger and bigger. So this ends up being a 1/2 power here, or 1/2 result, excuse me. We can continue going through a couple more with exponentials and logs. We'll take a look at the log function first. So if we consider, again, as x goes to infinity, this limit as x gets really, really large for the function ln, or natural log of 7x squared minus 100, let's just remember that natural log just takes a number and outputs another number. This natural log function, if we considered kind of the shape of this graph, just a regular ln of x, we can consider is undefined at an input of 0, but otherwise is an increasing function. So at natural log of 1 would be 0, and the function has a shape that increases gradually to the right. So this is the inverse function to the exponential function. So if this is natural log in blue here, we could say that the exponential, we'll call this y equals e raised to the x, this will be helpful as well, would have the input 0, 1, and it would be an exponential increase function that does not cross the x-axis. So there's our e to the x. Again, this is the point 0, 1, and we have the point 1, 0 on our other function here, the natural log. So these are inverse functions. They are reflected across this line, y equals x. And this gives us a good idea of what's happening to these functions as x trends to positive or negative infinity for both cases. So if I considered this limit for this natural log function as x gets really, really large, notice that with our blue natural log function, as x gets really, really large, we are increasing here. As much as I've kind of drawn this graph, it's increasing gradually, but we are increasing again here without bound for that natural log function. I could probably edit this just a little bit to make my point more clear. This is going to be, again, just increasing gradually here without bound for that one. So if we have any function here, 7x squared minus 100, well, this is an increasing function inside. And so as x gets large, the inner argument here, we'd say, in the natural log is also getting large. So we'd say that this quantity is tending off towards infinity here. So this limit would go to infinity. If I consider a expression I here that has a exponential function as x goes to infinity, we'll have kind of some similar arguments here. So first, let's just compare the numerator and denominator functions. We have e to the x. We know the shape of this function. As x gets really, really large, this is going to increase without bound very quickly. The denominator has a fourth degree polynomial, x to the fourth, which again here, as x gets really large, x to the fourth does increase and it gets very large, but it's not going to be as fast as an exponential function. Exponential functions, as x goes to infinity, will always be larger than these polynomial functions. And so we're really just doing a comparison test here of which is going to grow larger. And in this case, the numerator function, the exponential, will overpower that denominator. And so this will also tend off towards infinity. And you can check this again with a graph, but we'll want to make sure that we can know this on paper here to consider this comparison test. So exponentials will grow faster than our polynomials. The last one, part M here, still describes a limit as x goes to infinity, but now we're taking a look at a ratio that includes x to the negative x, or e to the negative x. So one way I can consider this is just by quickly rewriting this function, and we'll rewrite this in a useful way with the limit as x goes to infinity of 1 divided by e raised to the negative x. We could rewrite this as 1 over e to the x. With that negative exponent, we can bring e to the x to the denominator as a positive exponent, ex. And then we'll be adding 7 to that. So we've already said what happens to this e to the x term as x goes to infinity. E to the x also tends off towards infinity. So if this is a ratio here of 1 over something very large, again, in this exponent here, well, 1 over something very, very large is actually tending off towards 0. The larger our denominator gets, where we have a fixed numerator, we will have a really a 0, or a value of 0 that it will tend towards. So this quantity here overall actually tends off towards 0. So what we really have here is a constant 1 divided by 0 plus 7, or in this case, we'd just be left with that 1 over 7, because 1 over e to the x will tend off to 0 as x goes to infinity. So 1 over 7 would be our result. All right, so that would be the rest of our limits here. So thanks for tuning in, and I'll see you guys in the next video.